All right, well, hello everyone, and welcome back. In today's video, we're going to continue our discussion on problem solving and look at a few more examples of using analytic and creative problem solving strategies. All right, so by the end of today's video, you should be able to explain the steps of both creative and analytic problem solving approaches. So, you should be able to identify ways that you can improve at critical thinking and problem solving. Many students find problem solving intimidating at first. And believe it or not, problem solving really is a skill that develops with practice. So, we'll talk about some ways that you can continue to develop and improve your problem solving skills. And finally, we'll do a couple example problems of using creative and analytic problem solving. So let's start with a random question. Here we are looking for the false statement. See if you can identify which of the following statements is false about critical thinking. Go ahead and pause the video. See if you can find the false statement. So, what did you think? So, the correct answer here is choice A. So, the statement is false. People who are good at critical thinking are smart enough that they're always going to want to try to back up their opinions with data. And you will find as an engineer or as a professional working in pretty much any STEM field, as much as possible, you're going to want to be able to back up your opinions with data because that is the best way to make sure that you justify your decisions and a really good way to convince your team and your boss with data that your decision is the right one. So choice A is the false statement. The other choices here are all true. So let's briefly review what we covered from our previous video on problem solving. If you need a refresher on these approaches, you might also find it helpful to go back and review the previous video. So last time, we reviewed the strategies covered in our textbook, Engineering Your Future. There are many different variations on these problem solving approaches, but our textbook proposes the following 6 steps. First, we should define the problem and make a problem statement. Really, the goal here is to make sure we know what problem we're solving. Then we diagram and describe. We want to make sure we understand and can visualize our problem fully. Next step for analytic problem solving is to apply theory and equations. Remember, the analytic problems are very clear-cut problems, and usually they have just one solution. So if you have an analytic problem, you'll probably need to apply some theory and equations in order to find that solution. As needed, you may need to simplify the assumptions you make. And finally, you can solve the problem and verify your accuracy to the required level. Last time, you may remember, we discussed how important it is to do your best to verify your accuracy. You're not always going to have a solutions manual or a textbook that will give you the answer. You want to be able to check and make sure that your work is accurate. So analytic problems are the problems that are very clear-cut, well-defined, and have just one solution. But in engineering, many of our problems require creative problem solving. Now remember, problems requiring creative problem solving are problems that are open-ended. and these problems might have many possible solutions. And in fact, sometimes there isn't even a best solution. Sometimes you just have to find a solution which will work given the constraints that you have. So many engineering problems end up requiring these creative problem solving methods because they are open ended and complex. Once again, there are multiple different variations on these problem solving approaches. So, depending on who you talk to or what textbook you look at, there may be some variations on these steps. In our textbook, Engineering Your Future, the following 6 steps are recommended. First, we ask ourselves, what is wrong? We want to make sure we understand what the problem is. Then we ask ourselves, what do we know? And we gather as much data as we can. Number 3 is really important. What is the real problem? We want to try to identify the root cause of our problem. As much as possible, we want to be able to solve the root cause rather than a symptom of our problem. And remember, in our previous video, we covered 5 whys and structured problem solving. So I encourage you to try using these real industry techniques. Once we have identified our root cause, then we figure out, okay, what's our best solution? May need to do some brainstorming if needed. Once we decide on the solution to pursue, then we figure out how to implement the solution. And we finally need to evaluate and verify, did we solve our problem? So once again, these are a really good set of steps to follow to help you plan and tackle more complex creative problems. There's one more point we want to review from our previous video. You may recall that part of the creative problem solving process is identifying the best solution. And often, as part of the creative problem solving process, we need to brainstorm to generate ideas. So, our textbook recommends these nice guidelines to help us with our group brainstorming sessions. So, keep these guidelines in mind next time you're working with a team on a problem. Having a facilitator to take notes, defining the problem, and remember to keep the group small. You don't want to have too big of a group. Follow a set process. Write ideas down so that everyone can see them. Involve everybody. Don't dismiss the crazy or dumb ideas. Eliminate duplicates. And consider having everyone pick their top 3 choices that came out of that brainstorming session. Last point we covered at the end of our video last time was critical thinking. And we mentioned that critical thinking is a really important skill to develop. As many of the problems we're going to encounter in the real world are not solved quickly and easily. They may take months or even years to solve. And unfortunately, we are all human. We all have biases and experiences that can limit our thinking. So, the idea with critical thinking is You want to be able to continuously ask why and view problems objectively. And by trying to develop these critical thinking skills, you can become a more effective problem solver. So, in today's class, we're going to continue this discussion of first, how do we improve at problem solving and critical thinking? And then we'll go ahead and test drive some examples of analytic and creative problem solving. And if you have any questions on these topics, remember you're welcome to reach out. So let's go ahead and first cover how do we improve at problem solving. All right, so how does one improve at problem solving? Well, let's consider a couple points. Okay, so first, it's really important to remember that everyone starts somewhere, and everyone starts out as a beginner. So, especially for those who may be new to engineering and problem solving, please don't be discouraged if you don't have a lot of experience right away. Problem solving is a skill that you develop over time. Lots of research has been done on what makes people better problem solvers. So, it turns out that by looking at this research, we can get a better sense of what we need to do to improve at problem solving. So, I like to tell people that problem solving is like running. To get better at running, you ultimately need to run. Reading about running, watching other people run, or watching videos about running will only get you so far. To improve at running, you need to run. To improve at problem solving, you need to practice problem solving. So do lots of practice problems. And give yourself time to improve. This is not a skill that you will learn overnight. It is a skill that we develop over time. Another way to get better at problem solving is to adopt the habits of expert problem solvers. And so, one thing that we can do to improve our problem solving skills is compare what novice problem solvers do and what expert problem solvers do when faced with problems. And so, one thing you can do is try to adopt more of the habits that expert problem solvers do, and most likely these will help you become a stronger, more effective problem solver. And let's face it, we're all human. Nobody can be a perfect problem solver all the time. It's inevitable that we're going to make mistakes, we're going to be human. But as much as possible, try to use these strategies. View problems as an opportunity to learn and grow, and you may find that your problem solving strategies and skills will continue to improve. Let's go ahead and review some approaches that novice and expert problem solvers use. So here's our first three habits. So you can see in the left column, we have a characteristic. Then we have the novice approach and the expert approach. So first one is attitude. A novice problem solver has an attitude that might not be quite as strong. A novice problem solver will try once, then give up. Novice problem solvers are afraid to ask questions, and they're afraid to ask for help. This is also a common trend I see in students who tend to struggle in classes. They're afraid to ask questions, afraid to ask for help. In contrast, expert problem solvers are persistent and confident. They have what we call a growth mindset. They view problems as opportunities to learn. Expert problem solvers will attempt the problem first before asking for help, but if they do get stuck, the expert problem solvers will ask questions without hesitation. And as an instructor, I can tell you that some of my strongest students, the best performers in my classes, are the students who are not afraid to ask questions. Next characteristic is attention to detail. This is huge. I can't tell you how important attention to detail is to engineering. Novice problem solvers lack attention to detail. Novice problem solvers will forget to read directions. They may not read all the materials provided to them. They'll forget units and they'll make math errors. In contrast, expert problem solvers will read the directions very carefully, and they very carefully understand what the problem is asking. Expert problem solvers will also remember units and check and correct math errors. Imagine if you were a customer and you were trying to hire an engineer to solve your problem. Would you rather have someone with poor attention to detail or someone with strong attention to detail? Hopefully, you would rather hire the person with the good attention to detail, right? So try to be that engineer. Be the engineer with the strong attention to detail so that you will have stronger problem solving abilities. This characteristic is strategies for more difficult problems. Novice problem solvers will try to find the answer in the back of the book, or they'll search online. They will try to plug and chug into equations. They just seek the answer without trying to understand. Meanwhile, an expert problem solver will break the problem into smaller parts. They'll use problem-solving strategies to solve problems, rather than blindly plugging into equations that they do not understand. This is why it's really important to learn the problem-solving strategies we've covered. If you apply problem-solving strategies, you may be able to tackle more difficult problems more easily. All right, next three characteristics. Drawing a picture and diagram. This one is another big one. Novice problem solvers will rarely, if ever, draw a diagram or a figure. And unfortunately, this means that they're generally less able to visualize the problem. In contrast, experts always draw a diagram or a schematic to understand the problem. Always try to draw a picture and fully understand the problem you're solving. It will allow you to digest the problem, understand the knowns and unknowns, and arrive at a better solution. On exams, drawing a picture or a diagram might also help you get more partial credit if you answered a question incorrectly. So always try to draw a picture. Next one is memory and organization. Novices will attempt to memorize, but they won't really understand the key concepts. And you'll see that a novice problem solver has disorganized notes and calculations. On the other hand, expert problem solvers will seek to understand the underlying concepts rather than just memorizing. Memorizing can only get you so far. You have to understand the tools that you learn so that you can apply them to complex problems. Expert problem solvers also have very well organized notes, and the work they turn in is very neat and organized. Think about which engineer you would rather hire, organized or the disorganized one. Next approach is just the general problem solving approach. the problem solver uses. A novice problem solver might follow an unclear path and not show any work. Meanwhile, an expert problem solver will follow a clear procedure and strategy. They'll show all their work and they'll clearly identify knowns and unknowns. You can tell that the expert problem solver is really trying to understand the problem and solve it correctly. Once again, these habits are really important. And the more you adopt the habits of an expert problem solver, the more likely you are to improve further and gain even stronger problem solving skills. All right, here's our last list of novice versus expert problem solver skills. First one is what to do when you're stuck. Novices will tend to guess, or they'll just leave the question blank. As an instructor, I can tell you that it always makes me really sad when I see students leave questions blank. You should always make an attempt. Write down what you know. Ask for help. Do the best you can to find a path to a solution. That's what experts do. Expert problem solvers persevere. They brainstorm and draw diagrams. They apply strategies. And once again, they're not afraid to ask for help. As far as behaviors, novices, they tend to sit and think. They're more passive in reading the book. You'll see that expert problem solvers tend to be actively drawing and sketching. They use paper and pencil to draw out what's happening. And they might even be talking out loud to their teammates or to themselves to really ask questions and understand the problem. Next one is making mistakes. Novices will tend to either ignore their mistakes or maybe get discouraged by their mistakes. In contrast, experts will learn from their mistakes and even develop new methods based on their experience. So, as much as possible, you want to try to develop this growth mindset where you see problems as opportunities to learn and grow, and you're able to keep improving. Finally, last point, accuracy and evaluation of solution. Novice problem solvers will not proofread their work, and they don't necessarily think about their answer. They write down a number and they move on to the next question. Meanwhile, expert problem solvers are very accurate. They double check their calculations and they use their engineering spidey sense, intuition, to help check their work. So, just to summarize, there are kind of a list of 10 habits of highly effective problem solvers. So, I don't expect you to memorize these habits. I don't expect you to wake up in the morning and have all these habits perfect. But as you go through your career, both in school and in the real world, try to adopt more of these habits. These habits will serve you incredibly well, not just in engineering, but in any career path where problem solving is important. And of course, if you have any other questions on how you can further develop and improve these skills, I'm more than happy to discuss it with you. Please keep these skills in mind, especially as we move on to some sample problems. So before we dive into our sample problems, let's just briefly touch on critical thinking. So there's a lot of great resources on the internet about critical thinking. I've linked to a few of them on this slide. And let's just briefly summarize what is critical thinking. One definition says that critical thinking is self-directed, self-disciplined, self-monitored, and self-corrective thinking. Basically, you are able to look at problems objectively and efficiently without letting your own personal experience or bias affect your judgment. So, critical thinkers will ask questions. They'll raise questions early and precisely. They gather and assess relevant information. They come to well reasoned conclusions and solutions. So, they're really making sure, testing their solutions, making sure everything makes sense. They think open mindedly. So, they're always questioning their assumptions, the implications of what they're thinking, and the consequences of their solution. And notice this last one. They communicate effectively with other people to solve complex problems. So, once again, developing these critical thinking skills can be incredibly useful. So, why does it matter? So, critical thinking allows you to form your own opinions. And so, once again, just being able to regurgitate what the textbook says, that's not going to get you very far in engineering. Also, it allows you to craft arguments and back them up. If you need to design something new, or if you want to do original research, like in graduate school or in a PhD, you need original critical thought. Critical thinking also helps you evaluate your own work. So, again, it leads to better grades, which is a good thing, better habits of mind. Critical thinking allows you to continue to develop after you graduate. And this way, when you encounter new information, you'll be better able to evaluate and use that information. Also, it helps you make hard decisions. Unfortunately, people can and will manipulate you in the real world, and so being able to think for yourself can also help prevent people from taking advantage of you. And of course, critical thinking makes you a stronger problem solver, so you'll be more employable and probably better paid. If you'd like more information on this, I highly recommend you check out these links on critical thinking skills. And finally, I'll end with sharing some top ways to become a better critical thinker. And once again, these are some very good habits to keep in mind as we solve our practice problems. So notice what these habits are. Asking questions. Validate your assumptions. Make sure your assumptions are reasonable, right? Also, identify the real problem. There's that root cause analysis again. Be resourceful. Look at all the data. Make and follow a plan. Resist the urge to cut corners. Identify and thoroughly validate your leading solutions. Make sure they will solve your problem. Also, remember nobody thinks critically 100% of the time. We're all humans. We're not machines. We also want to make sure we think for ourselves and that we're able to present data clearly and effectively. So try to develop these skills. And as you approach more and more problems, see if you can use those problems as opportunities to develop these skills. I don't expect you to memorize all these habits, but once again, try to adopt these habits. They really will serve you well. So, with that, let's go ahead and move on to some actual examples of analytic and creative problems. These examples are adapted from our textbook, Engineering Your Future. So you can also check out our textbook for more examples. And I also encourage you to find additional problems that might be interesting to you. So here's an example of an analytic problem. So here we are told we have a spherical balloon. You want to inflate the balloon so that the total surface area is 1,000 square inches. Currently, the balloon is inflated to a radius of 5 inches. So the balloon's been inflated a little bit, but we need to inflate it more until it reaches the desired size. We have an air pump which can pump air into the balloon at a rate of 10 cubic inches per second. So our question is, how long will it take for the surface area of the balloon to reach the desired value? For the purposes of this question, we are told we can assume temperature and pressure of the balloon remain constant when the air is being pumped. So this is definitely an example of an analytic problem because we are looking specifically for how long will it take for the balloon to reach the desired size. So let's follow our steps for analytic problem solving. Let's go ahead and follow these each one by one. So first we define the problem. So our problem is we have that spherical balloon and we want to calculate how long will it take for the balloon's surface area to reach 1,000 square inches. Again, we're assuming that we're pumping air in at that rate of 10 cubic inches per second. So we're making sure we are indeed solving what the question is asking. Our next step is to diagram and describe. Here is where we want to list all the information we know about our problem. And this will also help us make a plan to calculate whatever unknowns. So here's what we know. We know that we have a spherical balloon, so we can draw a sketch. And so we know our initial radius of that balloon. That's basically the distance from the center to one edge. Our radius is 5 inches initially. We are able to pump air into this balloon at 10 cubic inches per second. And we want the final surface area to be 1,000 square inches. So notice we don't know the final radius of the balloon, at least not yet. But we do know the final desired surface area. So now that we've kind of visualized our problem, we can see that we need some sort of way to relate the radius of our balloon to this surface area. And we need to figure out how much air and how long to pump to reach our desired size. So we've got our diagrams and our information. Now it's time to apply theory and equations. Thankfully, the equations for this question are fairly well known. We know that the surface area of a sphere is given by 4 pi r squared, where r is the radius of that sphere. We also know that the volume of a sphere is given by 4/3 pi r cubed. Again, r is the radius. And then, of course, pi is approximately 3.14. Another equation that we know is change in volume relative to flow rate. So notice here we can write the change in volume, or delta V, is equal to our flow rate, which is Q. Notice our flow rate in this case was given to us. Flow rate is 10 cubic inches per second. Times T, where T is our time, in this case in seconds. Notice if we were to do dimensional analysis, 10 cubic inches per second times T seconds, that gives us our flow rate Q is 10T. And we can see that the units for our change in volume would be cubic inches. So our goal here, once again, is to calculate how long we need to pump air. Now, what's this time T? So that the balloon's final surface area is 1,000 square inches. So the general strategy we can follow is first, we want to calculate the final radius of the balloon using the surface area equation. Then we can calculate the final volume. Then we can determine delta V by subtracting the final minus the initial volume. Once we know how much we need to increase our volume, we can determine that delta V is equal to our flow rate, which is 10 cubic inches per second, times T, so we can solve for T. Let's take a look at our next step now, which is simplifying our assumptions. So you'll remember in our question, we were told that we could assume the pressure and temperature of the air in the balloon remain constant. If you've done any work with ideal gas law or in chemistry class, you might remember that if pressure and temperature change, that could affect the volume of the balloon. And so for the purpose of this question, we're told we can assume that pressure and temperature are not changing and not affecting our balloon volume. So because of this assumption, we can go ahead and just perform our calculations. We don't need to do any corrections for non-ideal gas effects. So let's move on to step 5. Now we need to solve the necessary problems. So here's the proposed plan. As mentioned before, we can determine what radius and volume the balloon will have once it's reached that desired size. We can then determine how much volume we had initially and find how much we need to increase the volume in order to reach that desired size. Remember, delta V will just be the difference between the final volume minus the initial volume. Finally, we can use our equation. Delta V is flow rate times time, and our flow rate of 10 cubic inches per second. That will help us calculate how long we need to pump air into the balloon. Let's go ahead and try these calculations. So first, we need to determine what radius and volume we would have when the balloon has 1,000 square inches of surface area. So notice, in this case, we know the surface area value. We know 4 pi, we can solve for r. All right, so we plug in our surface area of 1,000 square inches, and we can solve for radius r. And so in this case, we determine our radius r is just 1,000 divided by 4 pi. And so in this case, our final radius will be approximately 8.922 inches. We'll worry about significant figures and rounding at the end of the question. So we know the final radius of our balloon. We can take that radius and plug it in to determine the final volume of our balloon. So in this case, we plug in that radius. So we plug in 8.922 for our radius value. And now we just need to solve for our volume V. If we crunch those numbers, we determine our volume V is approximately 2,974 cubic inches. Once again, we're going to avoid rounding until the end of the question. So we know the final volume of our balloon. Based on our strategy, the next step is to determine the initial volume. So we just follow a similar approach. We use our volume of a sphere equation, plug in 5 inches for our radius. Our initial volume is approximately 523 cubic inches. Now we need to determine the change in volume. How much do we need to increase the balloon's volume in order to reach our final size? We know the final volume is 2,974. Initial volume, 523 approximately. We have cubic inches for both, so we can subtract. We determine our change in volume needed is approximately 2,450 cubic inches. We're almost finished. Remember, the question is asking us how long we need to pump air into the balloon. So we need to pump air in until our volume has increased. So we need to pump air until the volume has increased by that amount. So to determine time, we use our equation delta V equals QT. We know we have a flow rate Q of 10 cubic inches per second. So we can plug in and solve for our time T. When we do this, we determine our time T is approximately 245 seconds or 4.08 minutes. And in this case, if we care about significant digits, we would recognize that we only have one significant digit in our flow rate. So our time would be expressed with one significant digit. We would say that it takes about 4 minutes in order to inflate the balloon. Finally, our last step is to verify the accuracy. Let's do a quick sanity check. If we pump air for 4 minutes, that's about 240 seconds worth of airflow. And in 240 seconds, we would increase our volume by approximately the right amount of 2,400 cubic inches. So this result seems reasonable. Had we calculated pumping for 4 hours or 4 seconds, maybe the answer would have seemed a little bit off. It's still a very good practice to check your work, check your units, make sure your result seems reasonable. So this is a good example of solving a problem using an analytic problem-solving process. If you were to see a question similar to this on an exam, make sure you know how to follow those 6 steps. And remember that the necessary equations would be provided to you on an exam. So that was our example for analytic problem solving. Let's now look at our last example for creative problem solving. This one is also adapted from our textbook, Engineering Your Future, and it's a good example to apply our creative problem solving process. So here we're told that a chicken epidemic has emerged in a rural area. You have been hired to stop the epidemic from spreading further and affecting more chickens at farms in the area. Thousands of chickens have already been infected, but the Environmental Protection Agency has mandated that infected chickens cannot be thrown away in the landfill or buried. Your task is to develop a plan to safely dispose of the infected chickens and stop the epidemic from spreading. So in this case, let's go ahead and apply our creative problem solving process to solve this problem. So first we ask ourselves, what is wrong? All right, so if we read the information we've been given, we can come up with a few points here. The initial thing that's wrong is that thousands of chickens must be disposed of because they're infected with disease. We also can't bury or throw them away, so we need to find a plan to dispose of them safely and to contain the epidemic. So next step is to identify what we know. So we know that we can't put chickens in the landfill or bury them. We have thousands of affected chickens that we need to dispose of. The area is known for chickens. So there may be farms around which are trying to protect their chickens from disease. We want to avoid spreading disease to the other chickens. There are also potentially a lot of chicken processing plants in the area. Chicken will spoil quickly if not refrigerated. We know we may be able to kill off the disease by cooking or burning the chickens. And the area is rural, meaning that there's not a lot of people around, and there may be more open space and farmland available. We also can assume that because it's a government agency, Environmental Protection Agency probably does not have a lot of money to throw at this problem due to potential budget cuts. So that's what we know. Let's now identify the real problem. To do this, let's ask 5 whys. Remember, in the 5 whys technique, we keep asking why 5 times or until we arrive at the root cause of our problem. So first, why can't we dispose of chickens in the landfill or bury them? Well, if we think about it, probably because the epidemic might still be able to spread to other chickens. So we don't want to contaminate the groundwater or the environment in the area. Okay, well, why might the pandemic still be able to spread? Well, even if the chicken is dead, the disease infecting the chickens is still present. And maybe it could still spread to the other chickens. Okay, then why could the disease still spread? Well, the disease is going to keep spreading unless we remove it from the chickens first. Okay, so why isn't the disease being removed from the chickens? Well, that would require us to treat the chickens with some treatment like heat, UV, or other biochemicals to disable the disease. Okay, well, why aren't the chickens being treated to disable the disease? Okay, well, it costs time and money, which the EPA doesn't have. Maybe we're not sure exactly what treatment would disable the disease, but maybe we could burn the chickens or cook the chickens. Maybe there's still a use for this chicken. So let's think about maybe the root cause of our problem is that we need to be able to remove the disease from the chickens in order to contain this problem. So, what's the best solution? Here is where we would do a brainstorming session. If you had a team, maybe you would discuss it with the team, do some research. Here's an idea for one possible solution. We could prepare biohazard bins and allow farmers to dispose of the affected chickens in some contained bin. And we would need to communicate procedures to quarantine the affected chickens and help farmers prevent their chickens from being infected. Then we also need a way to dispose of the affected chickens. So in this case, we could burn the chickens potentially. Maybe we figure out whether it's safe to eat the cooked chicken. Maybe the chicken meat or the chicken carcasses could be used for another product. Maybe something like pet food or fertilizer, if it is safe to do so. Or, if you have enough money, maybe you could just pay another waste disposal company and let them take care of the disposal. Depending on the resources available, you may choose any one of these solutions or something else. So, which solution do you think would be the fastest and easiest to implement? Take a moment and think about it. So, based on the information that we've been given, I would guess that choice A would probably be our best option. Given that the area is very rural and that time and money might be limited, if we can find a safe place to burn the chickens to dispose of them safely without spreading disease, that might be the safest approach. How would we implement this solution? Well, implementation requires a lot of communication and planning. So here's one possible example. First, we probably need to communicate to all the chicken farms and give them instructions about how to protect their chickens. We'd need to provide a safe way to collect the infected chickens and also a safe area to burn them. We would also want to have some sort of tracking to monitor and make sure that the number of infections are being reduced. And most likely, we would need to get the Environmental Protection Agency to sign off and approve of this plan before we get started. Once again, this is just one example of how the creative problem solving process might be used. Depending on the problem and the information you're given, there could be many possible answers. There won't always be one best solution. But the important thing is to do the best you can with the information you have to come up with a solution which is safe and reasonable and solves your problem. Let's go ahead and wrap up for today. So, just to summarize, you should now be able to understand and explain the steps of the creative and analytic problem solving process. Also, we talked about ways you can improve at critical thinking and problem solving. As much as you can, try to adopt the habits of experienced problem solvers and experienced critical thinkers. You may find that by adopting those habits, you'll be able to improve at problem solving even more quickly. And finally, keep practicing. As we said, one of the best ways to improve at problem solving is to sit down and solve problems. So get practice and try applying the things we've covered in this video to the next problems that you encounter. And remember, problem solving is a skill that develops over time. So be patient. Give yourself that time to improve. Keep practicing, and you will definitely improve with time. Thanks everyone for joining the fun and watching today's video. We will see you all in the next one.